In this video, I'd like to talk about the math question of the day for Saturday, May 6th, 2023. And today is also my brother's birthday, so happy birthday to my brother Tom. Now, for this question, we need to find two positive numbers whose product is 750 and for which the sum of 1 and 10 times the other is a minimum value. And since we need to find a minimum value, that's our clue that this is an optimization problem from calculus. So at this point, go ahead and pause the video, see if you can work through this on your own. And when you're ready, unpause the video and we can go through this together. Now, assuming that you have attempted the problem, let's start working through it. And our first step is to define some variables. We're looking for two positive numbers. We can call those numbers just x and y, or whatever letters you want to use. And we know their product is 750. So when we multiply them together, x multiplied by y, we get 750. And we're also told that the sum of one of them and 10 times the other is a minimum. So we can use s for sum. We are adding them together. We have one of them, we can use either x or y, it doesn't matter, and 10 times the other one. So we're adding them, and the second term would be 10 times that other variable. We already used x, so it will be 10 times y. And we need to use this third variable s for sum because this is the equation that we will actually minimize. This equation here is our constraint. It's what will allow us to transform this to an equation with just one variable. But we need to minimize this. We need to figure out what the smallest value for this actually is with this given constraint. And like I mentioned, we will need to use calculus. Specifically, we will need to take a derivative of that. But I will come back to that in a moment. For now, let's focus on transforming this to an equation with one variable. And we can choose either x or y to actually substitute into this. It doesn't really matter. So let's maybe solve this for x. We can divide each side by y. We get 750 over y. And then anywhere we see an x, we will replace that with 750 over y. So that our sum is now 750 over y, or I will actually write this as y to the minus 1 power since we'll need to take its derivative, plus 10 times by y. Now, I mentioned taking a derivative since remember that if we have some general function, let's say that looks something like this, we can call this f of x. If we want to find either maximum or minimum values, we can use the derivative. Since remember that the derivative at some given point along our curve here will tell us how steep the curve is. It will tell us specifically, if we have a tangent line, what the slope of this line is. But in essence, it tells us the steepness of the curve at a given point. It tells us the rate of change of that curve. And notice that when we have maximums or minimums, the tangent line, if we draw that in, will just be a flat or a horizontal line. And that will be the case for the minimum as well. And at both of these points, we know that m, the slope, is equal to 0 for that tangent line. So if we find the derivative, we can just set it equal to 0 and figure out, in this case, what the y value would be at that point. And from there, we can figure out what the x value is. So let's take a derivative. We can look at the derivative of this sum, and we're taking it with respect to y. And of course, we'll set this equal to 0 at the end. Now, we will use the power rule. Remember, we can take this exponent, bring it down in front, and multiply. So minus 1 times by 750 would just be minus 750. And then we subtract 1 from this exponent. Minus 1 would just be negative 2. And we'll do the same thing here. We have y to the first power. We bring the 1 down in front. 1 times 10 is 10. And we subtract 1 from the exponent. And now we have y to the 0 power, which of course is equal to 1. So we just have this plus 10 at the end. And this right here is our derivative. We can set this equal to 0 and actually solve for y. So let me make a little bit of room here. And we can start by adding this negative term to the other side so that we have 10 is equal to 750 multiplied by y to the minus 2, or just over y squared. And to get our variable out of the denominator, let's multiply both sides of the equation by y squared. We get 10 y squared is equal to 750. Let's divide each side by 10. We get y squared is 75. And we can take a square root of everything, so that y is plus or minus the square root of 75. But you might remember from the beginning that y and x must be positive numbers. So we can exclude the negative part and just focus on that y is the square root of 75. And from here, we can figure out what x is. So we just found that y is the square root of 75, and x is 750 over y. So we have 750 over root 75. Now, of course, we can also rationalize this. We can multiply the top and bottom by that square root, root 75, so that in the numerator we get 750 multiplied by root 75 over root 75 squared, which is just 75. And these will simplify. 750 over 75 is just 10. So we get 10 times by the square root of 75. And if we want, we can even simplify the square root of 75. So that's just really 3 multiplied by 25 on the inside, which we can separate into 2 square roots. And we can actually take the square root of 25, since that's a perfect square, so that we get 5 root 3. And replacing root 75 with 5 root 3, this would become 50 times by the square root of 3. So we just confirm that x would be 50 root 3, and we already saw that y would be 5 root 3. And so this is what we think is our answer. And we could test it. If we multiply these together, we will get back 750. But to determine if this is truly a minimum value, we need to go one step further. And often, this is the step that students will neglect when optimizing. And if we remember our quick sketch here of f of x, we did find one value when we set the derivative equal to 0. We found that y was that square root of 75. And the problem is we don't know if we found the maximum value or the minimum value. It's possible we have a function like this where we actually just found the maximum value. And you could plug in values around there to see if it's more or less than the value that you found for the sum, but it will be better to use what's known as the second derivative test. Since remember that if you have the derivative, that tells you the rate of change of your function. But the second derivative tells you the rate of change of your rate of change, or the rate of change of your derivative. And notice that for, let's say, the maximum, if we look at points leading up to this maximum value, we're looking at the derivative here, so the slopes of these lines, notice that as we approach the maximum, the steepness of these tangent lines starts to decrease and goes all the way to 0. And then after the maximum, notice that these slopes become negative. And that tells us that the derivative is decreasing when we have a maximum. Or we can say that the second derivative, f double prime, is a negative number, since the rate of change of the rate of change, or the rate of change of the derivative, is decreasing along this hill here, this interval where we have a maximum point. But after we pass what's called the inflection point, notice that our slope of this tangent line starts to get bigger and bigger. It hits 0 again and then starts increasing again. So with our minimum point, or this interval here where we have a minimum point, we can say that our second derivative is actually a positive number. So if we truly have a minimum, then our second derivative will always be a positive number. And so that right there, that's our second derivative test. We just want to see if we take the derivative of our derivative, will it always be positive? And that will guarantee that the values we found for x and y, those are in fact minimizing values of this sum here. So let's take the derivative of this derivative. And now, should be more careful, we're not actually setting it equal to 0. We just need to take the derivative of this. So let me just make a bit more room. We can do that down here. We are taking the second derivative now of our original sum function, which we write as d squared of s over dy squared. But again, this is just the second derivative of our sum. If you want to write it like that with the primes, we can call this s with 1 prime. And we'll just use that power rule again. We bring the negative 2 down in front. The negatives cancel. 2 times 750 is 1500. Then we subtract 1 from this exponent, so that becomes minus 3. And the derivative of a constant is 0, since constants do not change. Their rate of change is 0. And from here, let's just rewrite this as 1500 over y to the third power. And if we allowed y to be negative, this could be negative. But we know that y has to be a positive value. And when we plug in some positive value and cube it, it is always a positive number. And 1500 divided by some positive number is always positive. So this is always greater than 0, meaning that our second derivative is always positive. And that tells us that this y value we find is in fact a minimizing value and not a maximizing value. So if we go back up, now we can feel very confident that this x and y value, they do give us a product of 750, and they do minimize this sum equation, where if we take this x value and add it to 10 times the y value, we know that that is in fact a minimum value for this sum. So we can feel confident that this is the correct answer.